All right.
One of the kids on one of these little streams to start with the iCarly theme song.
How does that go?
You know, as much as I would love to recite it for you.
Actually, I'm tagged with the road, but I'm not sure.
Okay. So this is a standalone problem set. It's just momentum. So it's kind of a short one. So you probably all heard that word, momentum, just used in like common parlance, just to mean kind of, something has some momentum, right? Like it's going to keep going. So let's just get into it here. I'm giving you the definition here. So momentum is P. And so Aiden had a good point, which was, well, if you're going to use the letter P for momentum, then you guess if you're going to do a physics problem or describe some physical system, and you want to talk about momentum and power, you got to be extra careful that power is capital P and momentum is lowercase p. Anyway, there's a definition. So then first thing to talk about is just what are some ways you can have a lot of momentum?
Your mass.
Big mass, right? So like a train has a pretty small velocity, but a very large mass. So a train has a lot of momentum, okay? And then, well, what about something really small that's traveling really fast, a tiny little meteor or something, like something that have a small mass but at a very large velocity and also have a large momentum. So the difference here with energy, because you might look at that and go, well, that kind of reminds me of energy, right? Energy depends on mass and velocity. But like with energy, kinetic energy, a little bit different though, because what does doubling the velocity do? Would quadruple the energy. Doubling the mass doubles the energy. So there's definitely a connection here between the two. So doubling your velocity would double your momentum, and doubling your mass would also double your momentum. So, and this is getting a little ahead of ourselves, but like I didn't want to mention this at the beginning. Why bother with this? Why describe this quantity? Why define it in the first place? Does anyone have a guess as to why would we bother to define this quantity? And the answer is it's kind of similar to the reason why we define energy in the first place. Anyone got a guess?
See how much is lost.
Sort of.
This is how much is like maintained, like something like
Yes. It's conserved. So it's going to turn out that we've been talking about, energy is conserved, right? Conservation of energy a lot. That actually allows us to analyze a whole bunch of physical systems by saying, assume the energy is conserved, so the total amount of energy here is equal to the total amount of energy over there. Same thing is true of momentum. And momentum is going to be conserved. The one really big thing that we're going to look at is in a collision. If two things bonk into each other, the momentum will be conserved. So, by the way, there's a really interesting. She's more of a mathematician than a physicist. She was a physicist. Emmy Noether. If you're interested in like the history and the people behind this stuff, Emmy Noether has a theorem that some people consider to be one of the bigliest theorems in like all of math and physics, which is she essentially proved mathematically that in a sense any universe you might construct is going to always have like these certain quantities that must be conserved due to symmetry. Anyway, she's just a lit savage. You should look her up. So, Emmy Noether. So, okay, well, this question is asking us to then define this thing called an impulse. Okay, so the impulse is going to be the change in momentum. So I'll show you a really exciting demonstration here. So this thing is sitting here, and I bonk it, right? Oh, I gave it some momentum for a second. Okay, and then of course friction took away the energy. as we were studying before. So what you might do is something like, well, how do we talk about the change in momentum? Well, most of the time, the mass is not going to change. When you hit something, you're not changing the mass of it. So what you can say is that the change in momentum is equal to the mass times the change in velocity. Do we feel okay about that? We're not done yet, but because it says, can we somehow relate this to like a force? When you exert a force on something, you're going to impart some momentum to it, right? That makes sense? Like this. I exert a force. I gave it some momentum when I was pushing it. So to start with this everyone understands going from here to here, right? Okay. Then this again just says something like, if you double the velocity, you'd be doubling the momentum. Now let's suppose we divide both sides by some amount of time, some time period. It could be 2 seconds, it could be 3 seconds, it could be a millionth of a second, doesn't matter. So some amount of time. Okay. So wait a second. What is it when you have a change in velocity over some period of time? What do we usually call that? Acceleration. So this right here is now an acceleration, right? So is everyone okay with that? So this says that the change in momentum divided by that period of time would be equal to the mass of the object times its acceleration. And what do we know about this? That's F net. So sorry, I think it's crooked. Okay. So change in momentum divided by time must then therefore be equal to the net force. And so our final result then is that the change in momentum, also known as the impulse, is just equal to the net force multiplied by some time period. You might also see this written like this. Like you might see it as a delta t. It's just kind of a choice of notation. Okay, so there's a pretty important formula for you, which is that yes, you can talk about the impulse on an object as the net force acting on the object multiplied by the time over which that force was exerted. Does that remind you of any other famous formula? Force times distance gives you work, right? So that's something worth kind of reviewing real quick, which is that so work is force times distance. When we learned that, you probably were like, well, man, force times distance, wouldn't it sometimes be better to talk about force times time? How much time was that force exerted for? Does that make sense? Not because how often are you like, oh, the force was exerted over this distance? That's most of the time, if you're like analyzing something, you'd be saying, well, how long was that force exerted for? How much time? So anyway, now we know. So this is for work, joules. This would be force times time gives you the impulse. And then what are the units? What are the units of momentum? Well, let's look at the units. What do we do? Kilograms times meters per second. Unfortunately, there's no fancy unit. I don't know why.
That is a bummer.
They don't go, oh, this thing's got this many goop gobs of momentum. They just say. Now, if you look at this, you could potentially write that as what? Newton seconds. Make sense? Newtons multiplied by seconds. Does that make sense?
Yeah.
Now, if Newton seconds make intuitive sense to you, then good job. It doesn't to me really, as far as right, because like meters per second, I can visualize in my head, oh, traveling a meter in a second. But a Newton second, I mean, the best I can do is say, well, based on this definition, a Newton second is how much momentum you'd gain if you had a Newton exerted on you for 1 second. That's the best I can do, right? Okay. How do we feel? How are our feelies? What are your feelies?
Good.
If you had to summarize your feelies in one word, what would it be? There's a right answer to this.
Good.
No, patriotic.
I failed.
Failure.
Take me off the.
Okay.
Walk on.
Gonna force you to watch
Walk on.
Stomp the Yard, You Got Served, and Step Up to the Streets. You don't get to see Step Up. You just have to watch the sequel. So the whole time you're like, who's that? I don't know who that is. I don't know if they introduced all new characters for the sequel. I never saw it.
You know, I couldn't tell you.
Anyway.
They had some of the characters.
This guy's a big step up.
He does all the stuff.
No, my mother forced me to watch them.
She
She always had
From
control
Asia.
of remotes, they were always on.
Kind of imagine you in like a Clockwork Orange situation where your like eyes are like,
Yeah.
like being forced to watch Step Up to the Streets. Okay, number 2. So we're going to look at what if you throw a bouncy ball against the wall? Can you figure out what's the force exerted on that ball without being able to like directly see it or measure it? So, by the way, you guys can all imagine like when a bouncy ball hits a wall, it compresses, right? In many ways, you can think of it kind of like a spring-like structure, because when that ball first makes contact, the ball's not really deformed much, but as it squishes against the wall, the ball is going to kind of deform, and as it gets more compressed, the force on the ball increases. Well, both ways. The force the ball exerts on the wall and the force the wall exerts on the ball both get bigger. Okay. So what they do, Trenton. Okay, so if the mass is, so this is number 2, if the mass is 0.3 kilograms, and it was traveling, so let's say, I'm gonna draw a picture here. So here's the before the collision. You got a 0.3 kilogram ball. Let's say it's traveling to the right at 35 meters per second. Okay. And then after it hits the wall, it's coming back. Now here's the thing. If you want to get really technical, be Mr. Actually guy, the definition of momentum, here's a good question of the day. What kind of quantity is that?
Speed.
Well, it's velocity. Velocity is a vector. I know the phrasing of that question was made it very, you had to kind of like read my mind, I get that. So anyway, velocity is a vector, right? It has a direction. So then what kind of quantity does momentum have to be? It's got to be a vector. So the point is that momentum is not like energy. Energy is not a vector. It's just a number. It's a scale, what they call scalar. Okay. Same with mass. Does mass have direction? No, mass is just mass. But momentum has direction. So that means it can be positive or negative, depending on the context you're working in. So in this case, what we're going to do is say, what was the initial momentum? Well, that momentum was mass times velocity. What is that going to end up being? 10.5. Okay. Is everyone okay with that? So we're gonna call this the positive direction for our purposes here. So the initial momentum is 10.5. How about the final momentum? Negative 10.5. Everyone okay with that? Technically, there's units here. They're 10.5 kilogram meter per second is the units. Okay, so this is asking for what's the impulse on the ball then? Okay, well, the formula for impulse is this. The impulse is the force times the time. That makes sense to everyone? So, but we could just directly get the impulse. What was the change in the momentum? Close. Kid one, that's good meme. Meme number. 21. Everyone understand that?
Yeah.
I mean, technically, maybe I should say it's negative 21, but it doesn't really matter. We get to the force exerted on the ball, points left, right? Yes?
Yes.
Everyone, are we sure everyone understands that where we're getting 21 from? There's no questions on that?
You just add the two together.
Just, well, I subtract them. So, in the simplest terms, the delta anything is just, it's the final minus the initial. Right? That's true of any quantity. What's delta banana? Well, change in banana would be, banana being some quantity. Right. That's just that's just what that delta means. Delta means the change in. So you subtract the initial from the final. So anyway, so the change in momentum is 21 kilogram meters per second. The force, we don't know what the force was yet. Now the time, how much time did this take place over? 15 milliseconds, it says. It only took 15 milliseconds for this ball. That's the time over which the force was exerted, right? So that's how long the ball was in contact with the wall. Okay, so the time would be 0.015. We okay with that?
And then you just divide.
Divide. Someone help me out with the calculator here. What does that come out to be?
1400.
You get 1,400. What are the units? Newtons. Okay. Do we feel okay about that? Now, there's a more nuanced consideration to make, which is, well, before I was talking earlier about how the ball's going to compress, right? So it's not like the wall just exerts a perfect 1,400 newtons for this amount of time, right? So what did we actually just calculate?
It's like the total force.
Sort of, yeah. It's the average force.
Oh.
So, so behind the scenes, imagine we had like a sensor in the ball or the wall. The wall might have a sensor in it that tells us the force over the time, right? So what would have happened was, right when the ball makes contact with the wall, there's not much force, but that force would rapidly increase. It would hit a maximum when the ball was at its maximum compression, and then that force would drop off as the ball was expanding and leaving the wall. Does that make sense? So the ball comes in, it's getting squish, 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 squish. It reaches maximum squishedness, and then as it's decompressing and leaving the wall, and this is the moment that it leaves the wall. So this period of time here would be like from time 0 to time 0.015 seconds. And what we just calculated was, well, here's one. What's that area? Force multiplied by time. No? Have I lost you? This area is the impulse. Does that make sense? So that's a general principle that we are looking at in this, in physics is hey, I got a quantity that's defined as this thing times this thing. So if I have a graph of this thing versus this thing, then the area under that graph, this is a calculus idea, but we can still use it without doing calculus. This area tells me this quantity. So then what we've just done, when we actually do this calculation, this is actually the average force. Do you feel feelies are intact? Okay. Let's maybe finish the page here. We got. Okay, so let's look at 3 now. Try to set up 3 on your own based on what we just did. A little bit different. This time we're solving for how much time did this event take place over if you know the average force and stuff.
What is your final answer would just be in seconds, right? Or would it be in milliseconds or something?
Just as appropriate. Like, so say you get an answer of 0.007. That's 7 milliseconds. You can convert it. Okay, so hopefully at least started with that, right? He had 60 units of momentum. And then after he came off the wall, he had the opposite, negative 60. Okay, so then you go, all right, well, the change in momentum is equal to the force, the average force, times the time over which that force is exerted. According to this, the change in momentum was 120. And it says that an instrument told us that the average force was 4,800. So when we calculate, we get, that's 0.025
Yeah.
seconds. And then Aaron had a great question, which is, well, should I write it like that or should I write it some other way? This is a valid answer. There's nothing wrong with this answer, but it's certainly good. You make sure you know how to go back and forth between units, right? So I think in this context, this makes more sense to write it as 25 milliseconds. So, and then the conversion there is very simple. If you wanted to say, well, how many milliseconds are there in this many seconds? You simply multiply this by 1,000, right? There's 1,000 milliseconds in every second. So, okay. You feel okay about that? Does that make sense? All right. Let's finish the page. We got. So 4, a couple more conversions here, just to irritate you, Trenton? It'd just be like that, right? Be like that. A 600-gram ball. So now the ball is 600 grams. What are we going to convert that into? Kilograms, right? So how many kilograms is that? 0.6. So this is the mass number we're going to use. That's going to play much more nicely with all the calculations and give us newtons and stuff as we expect. So if he's going 25 meters per second with that much mass, his initial momentum would be 15 units, 15. I'm not going to write the units out every time, but just because you guys are worth it. Kilogram meters per second. And as he's coming back, so it seems like he lost some energy, which is fine. So he's coming back at 15 meters per second. So his final momentum would be that times that, which is -10. Did I do it wrong?
No,
Oh,
no.
sorry, I'm dumb. Kate just looked at me like. No. Just testing you guys, obviously. So, same calculation. So what's the change in momentum? This is the common mistake. Just try to avoid this, guys. A lot of people will say it's 6. Just make sure you know that the difference between 15 and -9 is 24. So 24 equals the average force multiplied by, it says the time period over which this took place was 0.2 seconds, 200 milliseconds, right? 200 milliseconds is 0.2 seconds. We're sure we're okay? Yeah. Okay. And then so you divide by 0.2, and so what do you get? 480? Or what do you get?
120.
Huh?
120.
Thank you. Newtons. Have a good rest of your day.